As the global energy sector pivots toward decarbonization, decentralization, and digitization, virtual power plants (VPPs) are emerging as pivotal systems in reshaping grid dynamics. By intelligently aggregating distributed energy resources (DERs), VPPs deliver both energy and ancillary services to the grid through coordinated control. Leveraging advanced communication networks, control technologies, and software platforms, these systems actively monitor and optimize energy flows. The result: enhanced grid flexibility, responsiveness, and resilience. Yet, despite their transformative potential, VPPs face a complex array of operational challenges: grid integration and real-time responsiveness, cybersecurity vulnerabilities, interoperability across diverse systems, regulatory alignment, market access, and participation hurdles. To fully unlock the value of VPPs, stakeholders must embrace robust operational frameworks and adopt proven strategies that ensure technical scalability, reliability, and regulatory compliance. Virtual power plants (VPPs) represent a sophisticated approach to energy management, where geographically dispersed distributed energy resources (DERs) are aggregated and controlled as a single, coordinated power entity. This architecture enables flexible, efficient, and intelligent interaction with the grid and energy markets. Core components of a VPP DER assets include solar PV systems, wind turbines, electric vehicles (EVs), battery energy storage systems, and combined heat and power (CHP) units. VPP Platform, a software-driven system that orchestrates the real-time coordination, optimization, and dispatch of DERs based on grid demand and market signals. Communication infrastructure facilitates seamless data exchange between individual DERs and the central VPP controller, ensuring synchronized operation. Interfaces with grid and markets enable active participation in electricity markets and the provision of grid services, such as frequency regulation, peak shaving, and demand response. Types of virtual power plants (VPPs) can be broadly categorized based on their core operational objectives and functionalities. Commercial VPPs, designed primarily for participation in wholesale electricity markets. These VPPs aim to maximize economic returns by strategically managing energy generation and dispatch. Technical VPPs, focused on maintaining grid health, these systems provide crucial services such as voltage regulation, frequency control, and overall system stability, especially in environments with high DER penetration. Hybrid VPPs mixed models integrate both commercial and technical features to deliver economic value while actively supporting grid reliability. These VPPs balance market responsiveness with operational integrity. Operational challenges in virtual power plants (VPPs), distributed energy resource DER coordination and control. Managing a virtual power plant involves navigating multiple layers of complexity due to the diverse nature of DERs. Key challenges include resource heterogeneity. DERs differ in response behavior, storage capacity, generation patterns, and control capabilities. This variability poses challenges in achieving seamless, unified control across all units. Latency and real-time synchronization. Efficient operation requires tightly synchronized data exchange and command execution. Any latency or misalignment can impair responsiveness and grid stability. Dynamic forecasting complexity. Continuously predicting energy demand, generation output, and market prices is vital but inherently variable. Accuracy in forecasting determines the effectiveness of dispatch strategies and market participation. Grid integration challenges of virtual power plants (VPPs). As VPPs scale and integrate deeper into modern power systems, they present unique technical challenges that must be managed thoughtfully. Grid congestion and stability impacts. The deployment of large-scale VPPs can influence local voltage profiles and disrupt frequency stability, especially in regions with dense DER penetration. Inertia deficiency and system strength. Since most VPPs rely on inverter-based resources, they inherently lack mechanical inertia, a key component in traditional grid stability. This absence poses challenges in maintaining system strength and fast frequency response during disturbances. Interoperability and standards in virtual power plants VPPs. Ensuring seamless operation across diverse energy systems requires robust interoperability, yet several challenges persist. Proprietary protocols and system silos. Many DER platforms operate on closed or non-standard communication protocols, which obstruct seamless integration and limit cross-platform coordination. Absence of unified frameworks. The diverse nature of DER technologies demands standardized, interoperable interfaces. Without such harmonization, system-wide control and scalability remain constrained. Regulatory and market barriers facing virtual power plants VPPs. While VPPs offer promising pathways to modernize grid operations and democratize energy participation, significant regulatory and market obstacles remain. Undefined participation frameworks. In many jurisdictions, existing market designs do not explicitly recognize the role of VPPs. This lack of clarity hinders their formal integration and creates uncertainty around rights, responsibilities, and operational boundaries. Limited market accessibility for aggregated DERs. Smaller distributed energy resources grouped within VPPs often struggle to navigate complex bidding, settlement, and compliance procedures. This restricts their ability to fully participate in electricity markets and deliver value. Cybersecurity and data privacy in virtual power plants. As VPPs increasingly rely on digital connectivity and distributed control systems, safeguarding their infrastructure against cyber threats becomes paramount. Exposure to cyber threats. The expansive digital interfaces and communication layers within VPPs create multiple attack vectors, making them vulnerable to unauthorized access, data manipulation, and service disruptions. Sensitive data protection. VPP platforms handle large volumes of customer-specific energy data. Ensuring privacy and security demands robust encryption protocols, strict data governance frameworks, and compliance with regional cyber regulations. Economic viability and business models for virtual power plants. Despite their strategic promise, VPPs face notable financial and structural hurdles that impact adoption and scalability. Uncertain return on investment (ROI), high upfront costs for deployment, ongoing operational expenses, and compliance-related overheads can outweigh projected benefits, creating hesitancy among investors and operators. Incentive misalignment. Existing tariff structures and pricing models often fail to adequately reward distributed energy resources DERs for their grid contributions, thereby discouraging meaningful participation in VPP schemes.